Welcome back to ECE 442-542. Spring break is not yet, but it is going to be next week. And you won't be seeing me in office hours during that week. I hope that was sort of implied, but don't show up for office hours and expect to find me. I'll probably be somewhere else. Announcements. There's more than a page of those on the screen. The reading assignments, discrete equivalents are covered in two places in the course textbook, in Chapter 3 and Chapter 6. We will be talking about material that you will find in Chapter 6 in today's discussion. Chapter 3 deals with zero-order hold equivalence, which we talked about last time. This is actually lecture 4.4. Last time in class it was 4.1. In between those are these two pieces of material, lectures and videos. Lecture 4.2 deals with zero-order hold equivalence. It gives you a table that's different than Z-transform table, but it uses the Z-transforms to establish a table of zero-order hold equivalence. If I now said, oh, what's the zero-order hold equivalent of an integrator, you could go to that table and find that row, and then you know what that is in that particular row. Lecture 4.3 is actually split into two pieces. One piece is sort of this derivation of the zero-order hold with a state space representation. Last time we were doing it for transfer functions. Lecture 4.3 does it for a state space representation of a system, and B goes through an example. Those videos and lectures, I think the intent is to help you with the homework. Homework number 4 is due actually in 2 weeks, which means that it's due the week you return from spring break on a Wednesday. And there's some homework problems that are directly connected to those additional videos and notes, 4.2 and 4.3. The exam is in 3 weeks on the 25th of March. If you have questions over spring break or before the 16th which is basically the day we get back from spring break, put those into the quiz on D2L, and I'll try to address those in the exam number 2 review session, which is on that 18th evening, following our normal lecture period on the 18th, which is 2 weeks from today. If you've just been really anxious to figure out what the problem or the project consists of for this class, it's now available. It's at the bottom of the D2L content page. You can look at that. And there's really 3 deliverables, but 2 dates for those 3 deliverables. The first date is April 1st. That's deliverable number 1, and that really just means describe what you plan to do for your project. The other deliverables, 2 and 3, will revolve around the 3 different phases. Phase 1 is basically work the project, whatever that means, and there's different types of projects that you can pursue. Phase 2 is write up or basically package your product or project, whatever that means, and Phase 3 is associated with deliverable 3, which is a reflection paragraph. And Phase 2 and Phase 3 can be combined into one document, submitted into the Dropbox on the 6th of May. And I think that's basically the last day of class. Our final is, I think, the last day of finals in this same room, but I believe that's a Thursday, not a Monday or a Wednesday. Today what I want to do is get into the second type of discrete equivalence, which is scenario number 1, actually, relative to our block diagram discussion last time, and that is how do we do these discrete equivalents without worrying about the hold device that precedes our system that we are trying to take into the discrete domain. And you'll learn today that if we do it via a numerical integration strategy or technique, we'll do it three different ways: a forward approach, a backward approach, and the last one goes by many different names: a trapezoidal, a bilinear, or a Tustin. Essentially what you do is, if you had a transfer function, h of s, you simply replace all of the s's with these indicated expressions that are expressed in terms of z, where capital T is your sample period. And we'll derive those relationships. Where do those come from? That's the topic of today's class. How do we know, if we do a forward approximation, that we replace s everywhere with z minus 1 over t? And we'll try to go through some an example. And the example is one that I hope you're familiar with, is a low-pass filter. So that by the end of this period or session, you'll be able to find a difference equation associated with a low-pass filter using different types of numerical integration strategies: forward, backward, or trapezoidal. Maybe at the end we will look at how do we do this discrete equivalence by doing a pole zero mapping. Essentially, we map the poles in the S domain into their equivalent location in the Z domain using our buddy Z is equal to e to the st. We know that connection between the S domain and the Z domain. We now place, if we find our poles, those have a particular S value. Those now get replaced by poles in the Z domain, or Z minus e to the minus bt factors in the denominator. And what you will see is, in fact, this numerator has more than just a zero factor associated with mapping the zeros. This is now going, let me put in this is now an I sub z as an exponent, where that now is equal to the number of infinite zeros in your continuous time transfer function. And what you will see in the homework is that factor may be z plus 1 raised to the I sub z, where I sub z is the number of infinite zeros, and we'll talk about that today, or this I sub z could be, instead of I sub z, it could be I sub z minus 1 if you did this pole zero mapping or matching in MATLAB. Essentially, if you had two zeros at infinity and you found this discrete equivalent in MATLAB using the matching or mapping approach, they would actually use z plus 1 raised to the 2 minus 1, or just one of those z plus 1 factors. That will become clear, I hope, as we work through this. So that exponent that is being used to raise this z plus 1 factor, that varies depending on what we want to do. Whether we do it in MATLAB or we want to account for some kind of computational time in our implementation process. Now, if you had that factor z plus 1, I'm kind of getting ahead of myself, but where is the zero located associated with that factor at z plus 1? We set that equal to 0, and that says, oh, if we have a 0 at infinity in the continuous time case, then that maps to a 0, a finite 0, in the z-plane at z equal to minus 1. Or if we had two zeros at infinity in the g of s expression, we would have two of these factors, z plus 1, or two zeros at infinity, two zeros at minus 1 in the g of z expression. How many zeros at infinity do I have in that g of s expression? I'm talking about zeros at infinity like you know what that is. Let's see if we can just clarify that. How many zeros do we have at infinity in this g of s expression right there? And we're giving it the notation I sub z. What is I sub z for that transfer function? Anybody have an idea? How many zeros are at infinity? And what does that mean? That means that if we looked at s going off to infinity, would g of s vanish? Would it become 0? So if you look at s going to infinity in that expression, do you see that in the s plus a factor, the s dominates? And in the denominator, you have an s plus b times an s plus c. In each of those respective factors, the s's dominate as s goes off to infinity. As s gets large, as s goes off to infinity, do you see that that g of s really looks like s over s squared? Or if we divide out the s's, it really looks like 1 over s. How many s's do we have in the denominator of that eventual simplified expression as s goes to infinity? 1 over s. How many s's in the denominator? 1. So we have 1 0 at infinity in that g of s. I sub z would be equal to 1 in that example. And that's why in the g of capital G of z, you see 1 z plus 1 factor. We want to map that 0 at infinity into zeros at z equal to minus 1, which correspond to factors equaling z plus 1. Yes? So if you had another, the question was if you had another factor here, let me do it here, s plus d, then how many zeros at infinity would I have? I would have 0. So in that case, I sub z would be 0. Because as you let s get big, you have s squared over s squared. And those basically cancel effectively. S is going to infinity at the same rate in both numerator and denominator. And you don't have g of s going to 0 as s goes to infinity. It goes to 1. Or actually, in this case, it would go to k, capital K. Did that answer your question? Or if we didn't have any factors in the numerator except the k, what would our zeros at infinity be? 2, because we would have a 1 over s squared. Yes? Pardon? Can I sub z be negative? No, let's not really go there. Because we could divide out and basically find our our proper fraction that doesn't have constants associated with it. So zeros at infinity really makes sense when you have a proper or strictly proper transfer function. And we'll just focus on this class with I sub z being non-negative. Now that gets into the last part of today's class. I apologize if that's off track. Question? Pardon? Why is I sub z equal to 0 in this second example? So now I'm asking how many zeros do we have at infinity when I have upstairs a z plus a factor and an s plus d factor divided by, in the denominator, s plus b and an s plus c. If you let s go to infinity, what happens upstairs? Do you see that the S and the S get combined and you effectively have an S squared in the numerator? And in the denominator you have the same thing, an S squared. Now does G of S go to 0 as S goes to infinity? You have an S squared divided by an S squared. You've got infinity over infinity going at the same rate. That's a constant. And so it's not vanishing, so you have no zeros at infinity in this modified form of introducing this S quantity S plus D factor in the numerator. That's why the I sub z in the black is equal to 0. Now, moving back to this piece, which is the first part of what we want to talk about today, is discrete equivalence using numerical integration strategies. This is returning to scenario number 1, where we might have an analog controller and your boss now, she says, you know what? I'm tired of making these analog controllers, all these op amps and resistors and capacitors. I want to replace that with a digital device, a microprocessor, a computer. Give me a capital C of Z so that I can just insert it into my system. Obviously, you'll have to precede and postseed it by A to D and D to A conversions so that it's compatible with your analog system. But we now want to figure out, how do I replace capital C of S with a capital C of Z? This is discrete equivalent in scenario number 1 from last time. And do you see that in these red highlighted circles, I'm not incorporating any A to D behavior or D to A behavior. I just want to know what happens between the input and output signals of C of S and the input and output signals of C of Z, and I want to match those in some way. I want them to be, in quotes, equivalent. And you can see by our goals today, we have many different forms of equivalent. So they're not all going to be the same. They may give you similar behavior, but they will not be exact. So the forward method, the backward method, and the bilinear method will give you different results, but they will each be a discrete equivalent. Question?
So in this example, then, the only thing we're controlling is a digital C of Z, right? The user.
So now what we are trying to do is create or find or determine a capital C of Z. That's what we're trying to provide. Somebody is saying, I have a C of Z. I want you to give me, I have a C of S. Your task is to provide me a C of Z. So here it's stated just a different way. Discrete equivalent scenario number 1, and don't incorporate a hold device. We're now just saying the top block diagram, I want it to be similar to the bottom block diagram when I transition from a continuous time setting to a discrete time setting. I hand you a C of Z, you provide back, I hand you a C of S, you hand me back a C of Z. And there's many different ways of you producing that. And here they are. Today we're going to focus mostly on the numerical integration strategy, which we can identify 3 different ones today: a forward approach, a backward approach, and a bilinear or trapezoidal approach. And those descriptions will become clear, I hope, as we go through the derivation. At the very end, and we have already talked a little bit about this, is the pole zero mapping or pole zero matching. And that's really just replacing all of our poles and zeros that are at S locations with factors given by their poles and zeros corresponding to Z equal to e to the st, where t is the sample period and S are the respective poles and zeros. So what are we doing? In numerical integration, this is what we have. We now are doing exactly what the description says. We're trying to integrate numerically. Here is our time axis, and let's just draw a curve, and we'll call that curve x of t. Numerical integration, we are trying to find the area under that curve numerically. And the way that we will do it is by chopping up our time axis. And if we chop up our time axis, let's say here is time t minus capital T, and here is time t. Which, if I now say, oh, what's the area underneath x of t up to time t minus capital T, this point right there is x at time, well, let me say that we're now discretizing time, so we're really setting t equal to nt. We're chopping up our time axis. We're trying to do this integration numerically. If we now are looking at t at time t minus capital T, that actually corresponds, well, what does that correspond to? We're saying this is nt minus t. But that we can say is n minus 1 times capital T. Or the next time in our discretization of the time axis, this point t is in fact what we will just label little n capital T. Now, that means that x at time little t minus capital T can be equivalently written as x at time n minus 1 capital T. And this point right here on our x of t curve can be written as x of little n capital T. We're interested in the area under the curve. So up to time quantity n minus 1 times capital T, we want this area. And we are going to actually call that area y of t minus cap t, because that's really what this is. This is x of t minus x of little t minus capital T, where little t is replaced with little n capital T. Y is now the area underneath the curve up to time little t minus capital T. Now, if we said, well, what's the area under the curve up to time t, or little n capital T, that's now this. Do you see we've now added on a little bit more? But this, if I can find the lines properly, this is now y of t. That's our notation. And we actually want to evolve this in time so that as we march along and increase on our time axis, we want to get the next y of t from the previous y of t. what are we doing? We want to find the area under the curve, which is this in our classical integration expression if we let x be a continuous function of tau or time. We want to now chop that up. Y of t is the area under the curve which we're calling x of t up to time little t. That's how we've defined y of t. And maybe to be consistent, I should make that black. I don't know if you're going to be able to tell that from the notes, but you can use pretty colors if you want. What's y of little t minus capital T then? That's the area under the curve x of t up to when? Little t minus capital T. So this y of t minus capital T is the area. Notice I'm now writing in blue, trying to color code this so that it's maybe more clear. The area under x of t up to time t minus capital T. Can we now write y of t in terms of y of little t minus capital T? Y of little t is equal to y of t minus capital T plus what? If we were just doing this with calculus, what would be after the plus sign now? If we were doing this with continuous calculus, what would we add on to y of little t minus capital T? We would do another integral, wouldn't we? We would integrate x of tau d tau over what limits? From t, little t minus capital T up to t. And we're now letting t equal nt as we discretize it, so that now we are going to have y of t is equal to y of t minus capital T plus, and maybe I'll just do the following. Let me make this even more clear. Plus the integral, capital T becomes nt. This is x of tau d tau. And what's my lower limit? Little nt minus t, or that's little n minus 1 times t. That's saying the same thing. What are we actually doing? Well, in fact, what we are doing with these numerical integration strategies is using different strategies to actually compute numerically that integral. And what does that represent over here? Well, over in this diagram, we are now looking at figuring out what is this additional area, and how do we determine that additional sliver of an area? We can do it many different ways. We could do it by looking forward from x at time t minus capital T, and that would, in this case, overestimate that sliver at this particular point in time. Or we could look backward from t, or from little n capital T, and now that one would underestimate, but you can see how x of t, if it's doing a different dance, it could over or underestimate equally as well, depending on forward or backward. And then the trapezoidal is just what you would think. It's now doing basically an average of those two, but it's now saying, oh, let me connect the dots, and boy, just because of the way I drew that x of t, that looks pretty good in terms of the way it would approximate that sliver that's added on to the area under the curve up to little t minus capital T. Our goal today is just to derive relationships for integrating or approximating that little sliver of area. And I've just illustrated the three different strategies: forward, backward, and trapezoidal. Let's walk through that. Is that clear?
Sorry, I was writing when you said the sliver. What sliver of area were you talking about?
The sliver is now this red piece. Either it's a rectangle going forward, it's a rectangle going backward, or it's a trapezoid connecting the two endpoints. We're approximating that area by one of those three strategies: a forward approximation, a backward approximation, or a trapezoidal. Or they may call the trapezoidal a Tustin or a bilinear. Just letting you know on the terminology. Let's look at, well, do I need to add anything more here? The different numerical integration techniques are based on how we approximate that additional piece of area. And here's the forward rule. The forward rule is to approximate the integral with the rectangular area looking forward from x at time n minus 1 cap t. So now what I want you to do is tell me the expression, the formula, on the right-hand side of that approximation symbol. We are now trying to make this rectangular approximation of that additional piece using the forward approach. How would I describe that rectangular area? A rectangle has a width and a height, doesn't it? What's the width of that rectangle? It's little nt minus little n minus 1 times t. That's actually just capital T. The width is our sample period. The width of this is just capital T. What's the height for the forward? That's just x at little t minus capital T, but we've replaced little t with little n capital T. So that's now x at time quantity little n minus 1 times capital T. That's an expression that approximates that integral using the forward strategy. We now are saying on the right-hand side the approximation will be width times height. Or that now says that, oh, we now have our expression. We now know that y at time little n capital T is approximately equal, because we're approximating the integral, but it's approximately y of n minus 1 capital T plus that approximation, which is t x of little n minus 1 capital T. One reason why we've been talking about z transforms, now let's go into the frequency domain. Can we transform this difference equation in the time domain, which is what? This is a numerical strategy for finding the area underneath the curve x. So if somebody wanted to numerically compute the area under x, boy, don't you wish this was how hard calculus was when you were learning it? You just sit there and add. Multiply and add, multiply and add. That's what you're doing. Can we now take that into the frequency domain? Let's z-transform that time domain difference equation. What if I z-transform y at little n capital T? What does that become? It's so easy, it's hard. Just pull out your shift key. We're just capitalizing little y, right? We're saying take this from the time domain into the frequency domain. The z-transform of y of nt is now capital y of z. I'm going to just go ahead and say, let's call that equal to. Now what happens if capital Y of z is the z-transform of little y of nt? What's the z-transform of little y of n minus 1t? A one sample period delayed version of what we had before. That's now z to the minus 1 capital Y of z. If you that capital T, we lost it. Where did it go? No, it's kind of a placeholder. Sometimes we use it, sometimes we don't. But it's in the real system, we have to account for capital T when we are chopping up our time axis. But once we know what capital T is, sometimes we just throw it away and say, oh, I know this is y at time n, this is y at time n minus 1. And if somebody says, what's the actual time, then you have to tell them, oh, I was sampling at this capital T for my sample period. So if I'm now 100 samples into this iteration and capital T was 0.01, I'm now at 1 second in physical time. Now we will need capital T in the third term, which is a constant. So if it was 0.01, we have to put that in. That's 0.01. We can't throw it away. But in the argument of our x and y, sometimes we get sloppy and we just neglect capital T. Is that kind of what you were asking?
Yeah.
So now, what's the next one? Well, T is just a constant. That transforms, that factors right through the z-transform. And how do we transform x at time n minus 1? Are we comfortable with that? We've now moved into the transform domain. Let's now clean this up or put it in a form that we can actually find a transfer function. We want now y of z over x of z. Let's combine all of our y's. So we now have 1 minus z to the minus 1 y of z by moving that first term on the right to the left. And that's now equal to t z to the minus 1 capital x of z. Or if we now solve for y over x, let's divide both sides by capital X. Let's divide both sides by the factor 1 minus z to the minus 1. And we end up with t z to the minus 1 over 1 minus z to the minus 1. And how do we rewrite that? In terms of positive powers of z. Multiply by 1, right? Z over z. And in so doing, what happens in the numerator? We end up with a t, and downstairs we end up with a z minus 1. So in this case, where is our pole? At z equal to 1. It's the value of z that causes that denominator factor to vanish, or denominator polynomial to vanish. And we only have a first order factor. That now is our discrete time transfer function of an integration. That's an integral in discrete time. Let's compare that with what we know happens in continuous time. This is our continuous time expression. If we if we Laplace transform that, we get this, right? 1 over s, multiplication by 1 over s in the frequency domain is equivalent to integrating in the time domain. Y, capital Y of s is equal to 1 over s, capital X of s. Or we now can find our transfer function between the input, which is what? Our waveform, our continuous time waveform, that's x. Our output is the area underneath that waveform, y. That's just 1 over s. That's the transform expression in the frequency domain of an integration operation. So what? Well, now we can compare this transfer function with this. Here we have it in the continuous time setting, or in the S domain. Here we have it in the discrete time setting in the Z domain. We are now going to connect those. Let's compare the transform equations. In the S domain, it's 1 over S. What was it in the Z domain? Capital T over factor Z minus 1. So let's now put that in here. That's now T over Z minus 1. And maybe you're not used to standing on your head. Maybe you are, but typically it's easier to say, what's S instead of what's 1 over S? Here's 1 over S. It's T over Z minus 1. We know that relationship, but let's just solve it for S. Let's do the reciprocal on both sides. And now we can say that, in fact, if I had an S in a H of S expression, I can replace that S with the reciprocal of what I had in the first row, or just Z minus 1 over T. And does this sort of feel okay? S equal to 0 is the same as Z equal to 1 in the S domain and the Z domain relationship. That's what, when you leave this class, that one should kind of stick with you. Z is equal to e to the st. All right, so now, anytime somebody gives you an H of S and they say, give me a discrete equivalent, you now have at least one in your back pocket. You have one discrete equivalent that you can use. You can say, oh, everywhere there's an S in his or her transfer function, I'm going to replace each S with Z minus 1 over T. If you had an S squared, you would replace it with the quantity Z minus 1 over T, that quantity squared. As I promised, let's apply this to a low-pass filter. Here's a low-pass filter in the frequency domain, A over S plus A. Tell me about that. Now we're in the interview. Where's the pole of this low-pass filter? It's the value of S that causes the denominator to vanish. That's when S is equal to minus A. That forces the denominator to be 0. Yes?
When you say you have something like the previous example, when you said you had, I guess 1, 0 with 1 over S, how is that? Because I understand how you get it, but like, I thought zeros were enumerators.
So now the zeros are, the question was, I'm not quite understanding what you were talking about before with zeros. I was talking maybe about zeros at infinity. Now we want to look at finite zeros. We're distinguishing between two types of zeros. Zeros at infinity, which is when S goes off to infinity, and what you're used to thinking of, which are finite zeros. So now we're going to talk about finite zeros. Where is the finite zero in capital H of S? What finite value or values of S cause H of S to vanish, or for H of S to equal 0? What finite values of S? Can you find a finite value of S that causes H of S to equal 0? That's where you're looking at the numerator and saying, do I have a numerator polynomial in S that I can find the roots of and set S equal to one of those roots, and then I'll have it vanishing, and that will be a 0. That will be a finite 0. This first order low pass filter has no finite 0. How many infinite zeros does it have? It does have an infinite 0. So sometimes, some books, some sources, they'll say, oh, you've got a transfer function, the number of zeros equals the number of poles. Well, what they're combining are the finite zeros with the infinite zeros to get the total number of zeros. That now equals the number of poles. It kind of just rubs you a little bit wrong sometimes, but now you know what they're meaning. What's the DC gain of this analog filter? I heard an A. Somebody want a B? Or a C? Or another value? What's the DC gain? That sounds better. Let's go from alphabetical to numerical for a DC gain. Let's start with the first number, beyond 0. It has a DC gain of 1, doesn't it? Because the DC gain is taking H of S and letting S equal 0. And that's now A over 0 plus A, or that's A over A, which is 1. What you don't want to jump to, which is a possible option on exam number 2, is I might give you what's the DC gain, and I might tell you it's A in one of your multiple choice. Because what? That's the gain in the numerator. Yeah, that's it. Probably slow down, okay, and think through what you're being asked. Yeah, all the exams are going to be multiple choice since everybody loves those, okay? But it did distribute the class. I kind of know who's where in terms of behavior or performance on exam number 1. I want you to now shift that to where people are really doing better on exam 2 and all the other exams. H sub F, F standing for forward. How did we say we would find H sub F of Z? Now we take H of S, and for the forward rule, we said, oh, everywhere we see an S, we replace it with Z minus 1 over capital T. That's all there is to it. That means then, in this expression, we have nothing to change in the numerator. That's just A. There was no S in the numerator. But in the denominator, we had an S plus an A. And we could clean that up if we wanted to. This is actually the answer, an answer. If we wanted to, we could multiply by 1 and not change anything, where 1 now is capital T over T. That gets rid of that capital T underneath the denominator of the first term in our denominator expression. Now H sub F of Z is AT over Z minus 1 plus AT. Or it's AT over Z minus 1 plus AT. I want you now to answer some of the same questions we were asking for the analog case, for the discrete case. Where is our pole? Or do we have multiple poles? Where is the pole? We set that denominator equal to 0 and solve for z. Z is now equal to 1 minus AT. Does that make you feel good? No? Oh, wrong answer. Why am I asking that question? Where is that pole located? For a given A is the bandwidth of our continuous time filter, T is the sample period. Those are both positive numbers. We're taking 1 and subtracting AT. A is usually pretty small relative to A. So we're taking a small amount away from 1. Where's that pole? Is it complex? Not complicated. Does it have a no, there's just 1. And where is it? It's on the real line. And where is it relative to 1? It's a little to the left. Where is that? That's inside the unit circle. Okay, we started with a low-pass filter. We would expect that to be stable. We better have a stable discrete equivalent, and we do. We have a single pole just inside 1, which makes sense. It's not real fast. It's a low-pass filter. Do we have a finite zero? No, there's no finite zero. Boy, we're being kind of consistent, aren't we, with what was happening in the analog case. What's the DC gain? So now, H sub f of z, how do we find the DC gain? What value of z is DC in the z-plane? What was the DC gain in the s-plane? S was 0. What corresponds to s equal to 0 in z? 1. So now we evaluate this when z is equal to 1. When we do that, we have AT over 1 minus 1 plus AT. We have AT over AT. We have 1. Our DC gain is consistent with what it was in the analog setting. Woohoo! So you should be feeling really good. Don't you argue with me. So there's our forward rule. Do you see how we're going to do all these others? Let's speed it up a little bit. Backward rule. What's this one? This is approximating that little sliver of an area, but now we're looking backward in time from x at time nt. What does that mean our approximation is equal to for this integral? What's the width? That hasn't changed. That's still t. What's the height of that rectangle? It's now the rightmost side of that rectangle, which is x at time nt. Or, what is our expression? We now know that y of nt is approximately y of n minus 1 t plus tx of nt. Z transform that. Y of z is equal to z to the minus 1, capital Y of z, plus t, capital X of z. Do you see that it's now changed a little bit from the forward strategy. Our approach was now to find y of z over x of z, and that's now t over 1 minus z to the minus 1. Or, multiplying by z over z, we have tz over z minus 1. If we're comparing transforms, 1 over s compares with what? Integration in the frequency domain of a continuous time is 1 over s. In the z domain, what is that for this backward strategy? It's just what I have right there, which is tz over z minus 1. Which is a little different, which is fine. It's a different approximation to that little sliver. Now let's get off our heads. If we were standing on our heads, let's take the reciprocal. Now we have this is z minus 1 over tz. So that now, if we had an h of s, everywhere we have an s, we replace it with this expression for the backward approximation, z minus 1 over tz. So let's apply that to the low-pass filter. We don't have to redo poles and zeros of h of s. We know what that is. But now this is h sub b for backward of z. This is now h of s, replacing s with z minus 1 over tz. That now becomes a over z minus 1 over tz plus a. We can clean that up with a strategic choice for 1, which is tz over tz. And we end up with now h sub b of z is now equal to atz over z minus 1 plus atz. Or this now says, oh, we have a coefficient scaling z in the denominator that's different from 1. It's 1 plus little a capital T minus 1. And the numerator is atz. Where's the pole? Same strategy, you just set the denominator equal to 0 and solve for z. Z now becomes 1 over 1 plus at. My question remains, how does that make you feel? Great, that's a good answer. Why? Because a and t are both positive. We multiply them together. We get a positive number. We have something in the denominator a little bit bigger than 1. 1 over something a little bit bigger than 1 puts us inside the unit circle. What's our finite zero? Now we have one, don't we? We actually have a finite zero, and it's z equal to 0. What's the DC gain? We evaluate that with z equal to 1, and we end up with at over 1 plus at minus 1, or again, 1. for a DC gain. Poles in a slightly different location. We now have a 0 right at the origin in the z-plane, but that could be considered a very fast 0. And we have a DC gain that's the same. All right, now let's step it up a notch. Trapezoidal rule. Now we are looking at this sliver. The width is still the same, and this point was x of nt, and this point was x at n minus 1t. Or what does, oh, I didn't give my, I made that too big, didn't I? So I can clean that up a little. Now my trapezoid's a little smaller, but gives me a little bit more vertical room. How do I approximate the area of a, or how do I define the area of a trapezoid? What's the width? Capital T, and the area of that trapezoid is really the average of those two lengths, isn't it? It's x at time n minus 1t plus x at nt divided by 2. That's now how I'm going to approximate the continuous time integral. And this, really, if you look at it, it's like averaging the forward and the backward strategies that we just performed. This is kind of a Goldilocks approach. It's not too big, not too little. It's halfway in between. Trapezoidal, bilinear. Or this now says that y of little n capital T is equal to y of little n minus 1 times t plus, and let me change this up a little bit, that's capital T over 2 times x of nt plus x of n minus 1t. Haven't changed the complexity really of the approach. The expression is just involves a few more terms. Let's take this into the transform domain. And what do we have? Y of z equaling z to the minus 1 capital Y of z plus t over 2 comes straight through. Then we have 1 plus z to the minus 1 capital x of z. Everyone following where that came from? Just factoring out the common capital X. We can now solve for y of z over x of z, and we're left with now capital T over 2, 1 plus z to the minus 1 over the factor 1 minus z to the minus 1. Or, written in terms of positive powers of z, multiplying by z over z, we end up with capital T over 2. That can be out front, it can be upstairs, it's the same. Upstairs we have z plus 1 over z minus 1. Little different, but consistent with what we've done. Now how do we go in the comparison of the transforms? Now we compare an integration operation, which in the S domain is 1 over S, with this one, which is capital T over 2, z plus 1 over z minus 1. Or, inverting that, we now can say, oh, that's now 2 over t z minus 1 over z plus 1. So now, if you wanted to use the bilinear transformation or the trapezoidal numerical integration discrete equivalent, everywhere you have an s in h of s, you replace it with this expression, 2 over cap t quantity z minus 1 divided by quantity z plus 1. And you know what we're doing. Now this is h sub t. That's a t for trapezoid of z. That's now h of s, replacing s, or substituting away s, with 2 over t times z minus 1 over z plus 1. That now says that we have a mess. No, it's okay. We have a over 2 over t z minus 1 over z plus 1. That's getting rid of s plus a. Can we clean that up? Of course we can. We know how to multiply by 1. The 1 in this case is going to be t times z plus 1 over t times z plus 1. That's our informed choice of 1. That now leads to at times z plus 1 in the numerator over 2 times z minus 1 plus at z plus 1. But we can just combine like powers of z in the denominator. In the numerator, we already have it. At z plus 1. Downstairs, we have a 2 and we have an at that add together to form the coefficient that scales z. And our constant is now at minus 2. Where's our pole? This is now h sub t of z. What is that? Remind me. That's a low-pass filter in the digital setting using a trapezoidal numerical integration strategy. Where is the pole? We just set the denominator to 0 and solve for z. So that at minus 2, if we put it on the other side, becomes 2 minus at. And downstairs we're dividing by the coefficient of z, which is 2 plus at. All right. How does that make you feel? Not great? It's a little bit more involved, but it is less than 1, isn't it? We take 2 and take a little away from it upstairs, and we add a little to it downstairs. We are less than 1. We are inside the unit circle. Where's our 0? Do we have a finite 0? That's now at another fast location, which is z equal to minus 1. What's our DC gain? We replace z with 1, and we now have 2at upstairs, adding 1 plus 1 in parentheses. Downstairs we have 2 plus at plus at minus 2. We have 2at over 2at, or 1. Now, what do you think somebody might ask you? That's a vague question. Relative to, now we have these transfer functions in the z domain that are supposed to be low-pass filters. How do we find their frequency response? Or where would we look to evaluate or talk about the frequency response of these three filters? These are three low-pass filters that you could now take into the time domain and find a difference equation for. But now, how would we think about the frequency response for discrete time systems? How do you think about it for analog systems? If I now said, oh, talk to me or explain how you find the frequency response if I gave you a pole zero pattern in the S-plane. What are you doing? If this is now the S-plane, how do you find the frequency response for a given pole zero pattern? Here's the real value of S. Here's the imaginary value of S. We just walk up this imaginary axis. We evaluate our transfer function at S equal to j omega. What is that? Well, that's just replacing S everywhere in our transfer function with j omega. We're walking up that imaginary axis. We're starting at DC at the origin, and then we just increase frequency. That's just walking up that axis. What are we doing in, so this is, in a sense, we now are saying, oh, this is h of s equaling a over s plus a. We now are looking for its frequency response, which is replacing s with j omega. And we say, oh, you want to know how this system is behaving at omega equal to 1? You plug in omega equal to 1 and find the magnitude and phase. And that's how, it's just a complex number. What does that look like in the z domain or in the z plane? Do we have something similar going on? Where are we walking in the z-plane? Where is DC in the z-plane? S equal to 0 corresponds to what in the z-plane? Where is DC? Z equal to 1. So we're right there at DC. What are we doing? We are now saying, oh, we have h of z, and we want to now replace z with e to the st, but in fact we replace s with j omega. We're now evaluating this transfer function. We're replacing z with e to the j omega t. What's the magnitude of e to the j omega t? E to the j theta, where theta varies as when omega varies. What's e to the j theta? Euler. Cosine theta plus j sine theta. What's the magnitude of that? Cosine squared plus sine squared, 1. So we are now focusing on the unit circle. We are now moving around. I wish I could draw this better. This is now the unit circle. Right there is j pi over 2. What's this point? In fact, now what we are doing, instead of walking up the imaginary axis in the z-plane, we are walking around the unit circle and getting over to that point. Minus 1 could be thought of as an infinite frequency in the z-domain. That's as high as you can go. Now we've collapsed this infinite frequency axis in the continuous time setting into a finite little unit circle piece, a semicircular amount. And this actually corresponds to omega equal to omega sub s over 2. We'll have to, I just want to keep going and just keep going and going, but my batteries are probably running low. But keep that in mind when we now start talking about frequency response. We're now walking around the unit circle and evaluating h of z at particular locations on that unit circle to get or obtain a complex number which tells us how the magnitude and phase change at a particular frequency. We'll pick up there, and actually I think I've included a little discussion of pole zero mapping at the end of this that maybe I will fill in. I don't know. I'll see. Maybe I'll fill that in and you can look over it over spring break, but that's where we will pick up next time.